Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. Today on Exploration, we're going to depart from our usual format because I'm actually traveling. However, I wish everyone a happy holidays and happy New Year. Today on Exploration, we're going to devote the full hour to something called string theory, something that has been generating lots of publicity. Perhaps you've seen major articles in Newsweek magazine, Time magazine, the New York Times, specials on PBS, but now we have a counterattack. All of a sudden, we have book reviews featured in the Wall Street Journal, Newsweek magazine, saying, what's all the hype about? Well, today we have two very special guests. We'll talk about what this hype is all about. The first is my friend Brian Greene, Professor of Physics at Columbia University, author of The Elegant Universe and the Fabric of Space-Time. And we'll be talking to him about string theory, what it is and why it's generated so much excitement. And then our second special guest is Professor Lisa Randall, Professor of Physics at Harvard University. And she's also the author of a book called Warp Passages. And with her, we'll be talking about something called M-theory, which many of us believe is a successor to string theory. Now, let me say, first of all, that string theory is supposed to be the theory that eluded Einstein for the last 30 years of his life, a theory of everything. A theory which can unite the quantum forces with his theory of gravity, a theory which would allow him to, quote, read the mind of God. But the theory has had its ups and downs. The theory first started back in 1968 when two young postdocs in Switzerland stumbled upon what is called the Veneziano model, which set into motion something called string theory, which explains all, we think, the subatomic particles of the universe. The protons, electrons, neutrons, neutrinos, they're nothing but notes, musical notes on a vibrating string. The laws of physics are, in some sense, the laws of harmony of this vibrating string. Chemistry is nothing but the melodies you can play on these strings. The universe is a symphony of vibrating strings, and the mind of God is cosmic music vibrating through 11-dimensional hyperspace. Well, the theory has had its ups and downs. I remember back in the 70s when the theory fell out of favor. It was very difficult to get a job back then. Many of my friends actually were kicked out of the profession because you could not get a job doing this bizarre theory called string theory defined in hyperspace. In fact, we used to joke that the place to find string theorists is the unemployment line. Well, the tables have turned now. A theory which was once the pariah of physics, which was once considered science fiction and Twilight Zone, has now become the center of gravity of theoretical physics as we realize that the Big Bang was possibly a bang in hyperspace. Well, now the critics have jumped on the bandwagon, forming a counter-revolution of sorts. They say string theory has gobbled up too many positions, that you cannot get a position at Harvard or Princeton these days without being a string theorist. Well, I kind of smile when I hear these criticisms because I remember the bad old days, the days when other physicists used to snicker and giggle behind our backs whenever we talked about higher dimensions, unseen universes, and vibrating strings. So, well, let's face it, physics, like all human endeavors, has fads and fancies. Back in the 70s, string theory was definitely out of fashion. It was career suicide to work on hyperspatial theories beyond our familiar three dimensions. And now some physicists are bellyaching that too much attention is being gone into string theory. Well, my personal point of view is that the theory is actually not finished yet. We still are not able to test it. We're still not able to get concrete conclusions out of the theory. But that's just a reflection that the theory was discovered by accident and it's not in its final form. So perhaps, just perhaps, some young physicist, budding physicist listening to this radio program will be tempted to finish the theory. Well, once again, our first special guest is going to be Brian Greene, Professor of Physics at Columbia University, author of Elegant Universe and Fabric of Space-Time. And in the second half, we're going to bring on Dr. Lisa Randall, Professor of Physics at Harvard University, author of Warp Passages. Okay, now let's talk about the theme of your book. First of all, why did you write the book, The Fabric of the Cosmos, and why did you choose this concept, fabric of the cosmos?
Sure. Well, when I was writing my first book, The Elegant Universe, that was a book about the search for the unified theory. And in that book, space and time play a role, but they're kind of secondary. They're supporting characters. But I kind of found that when I was writing the book, it was as if space and time kept trying to take over. They kept trying to grab the spotlight. And I realized that there was another story that I felt I really wanted to tell, which would be the history, the story of space and time, going back to Newton through Einstein and the cutting-edge developments that we're engaged with today with unified theories like string theory or M theory. So I really just felt that there was this need to tell this story of our changing perception of the arena of reality. And that's what the book is about.
Okay, now let's talk about the Newtonian universe and the transition to the Einsteinian universe. The Newtonian universe is a very common sense universe.
Yes.
1 second on the Earth is a second on Mars,
Exactly.
is a second on Jupiter. Yeah. 1 meter on the Earth is 1 meter on Jupiter, is 1 meter in Andromeda. So now take us to the transition to the Einsteinian universe where all hell breaks loose.
Sure. I mean, basically Einstein shattered Newton's common sense picture, the picture that you just paint, where there's an absolute space that exists everywhere throughout the cosmos, and it's the same for everyone. And Newton said there's an absolute time that ticks forward in the same way universally for anyone, regardless of what they're doing. That common sense picture completely went out the window when Einstein discovered his special theory of relativity, because in special relativity, if, for example, you and I are moving relative to each other, our clocks, our watches will literally tick off time at different rates. Our brain processes, our heartbeats will beat, will tick, will go forward at different rates if we are moving relative to one another. I like to think of it's as if Einstein kind of shattered the universality of time in the Newtonian picture, and each of us picks up a little shard of time. It becomes our personal clock, and we carry forward with that into the future. So it's a very different picture of time, and in fact there's a different picture of space as well. Similarly, what you consider a meter and I consider a meter can be different if we are moving relative to each other. Very strange, but that's what relativity teaches us.
Now, therefore, paradoxes abound. Any freshman taking freshman physics immediately comes in contact with paradoxes. If the concept of length and time are not absolute, then you can have two people each shorter than the other, two people each younger than the other, and many classical physicists rip their hair out trying to contemplate people each being younger than the other. So have all the paradoxes of relativity been resolved? Yeah,
all of them have been completely resolved. They are often puzzling because, as you say, there can be examples where you look at a situation and you would think that each individual, say, would be younger than the other because each had a clock that was ticking at a slower rate than the other. But the solution to all of these paradoxes is relativity. It's relative. When you look at two distant beings, there is a distinct notion of time that applies to each. So you are comparing apples and oranges when you try to compare clocks that are separate from each other in space. The only way to truly compare two clocks is to bring them back together. And it turns out, and this is the crux of all of the solutions to these paradoxes, when you bring the clocks back together, you necessarily introduce an asymmetry. One clock, for instance, has to turn around to rejoin a clock that it initially was next to. And in that turning around process, the symmetry between the two clocks is broken. And indeed, one clock, in fact, a clock that went out and came back in its motion, will truly be the one that has less time elapsed on it compared to the one that stood still. All paradoxes evaporate.
So in other words, if two people are each younger than the other, to determine who really is younger than the other, you have to bring them together.
Exactly.
Right. Now let's talk about the direction of time. Einstein himself did not write that much about why time moves forward in a certain direction. However, we all know that dead people don't come out of the grave, get younger, and jump into the womb of their mother. We all know that broken eggs don't jump out of the frying pan and go into the eggshell. But there's nothing in the laws of physics per se at the microscopic level that prevents time from going backwards.
Yes.
So in your book, you have a discussion of the arrow of time. Could you elaborate?
Sure. The arrow of time is a real puzzle in fundamental physics because, as you say, we are all familiar with events going one way in time and not the reverse. You gave some very good examples, egg splattering, people aging, and so forth. It always happens in one direction. Now, you'd think that since that's such a basic feature of everyday experience, that you'd be able to see why that's the case from the fundamental laws of physics themselves. But regardless of which laws we look at, be they the laws of Newton, the laws of Einstein, the laws of string theory, the laws that you have developed, that I have worked on as well, all of those laws show a complete symmetry between forward in time and backward in time. The experience of time going only one way or the other seems not to be found in the basic laws of physics themselves, and that's a real puzzle. Now, when we study this puzzle in more detail, surprisingly enough, we find that the resolution requires us to look all the way back to the beginning of time, all the way back to the Big Bang itself. And we believe that the Big Bang had certain very special features. It had very high order. We, in the trade, of course, as you know, call it very low entropy. And we believe that this very order, this very low entropy beginning to the universe is what imprinted a direction on time. And we have been experiencing the drive to ever more disorder ever since that pristine starting point. I mean, as everybody knows, things typically like to get disordered. Your house typically gets messy. It never spontaneously becomes clean and so forth. That drive to disorder, starting with the highly ordered beginning with the Big Bang, we believe, is why events always go one direction in time and not the reverse.
Now, Hawking tried to take this even one step further. Stephen Hawking believed at one point that if the universe expanded and then contracted, that time would reverse itself.
Sure, yeah.
And that all this entropy stuff that we've been talking about would run the other way. However, I understand that Stephen Hawking has since renounced this version.
Yeah, it was a mistake. You know, everybody makes mistakes, and even Hawking, genius that he is, he did make a mistake and misread the mathematics to imply that if the universe were to expand to a maximum size and then start to contract, that in that turnaround, the amount of entropy in the universe would start to get smaller and smaller so that people would unage and eggs would unbreak and so forth. But in reality, that isn't what he now believes. It's not what anybody really believes. We do believe that entropy or disorder will always increase into the future regardless of how space expands, and therefore the arrow of time always points in one direction. It doesn't flip around.
So it's rather mind-boggling realizing that in some sense the reason why eggs splatter, it has to do with the origin of the universe itself.
Yeah, totally. That really blows my mind. You know, every time you drop an egg, it really is tapping into, it's reflecting a feature of the origin of the universe.
Amazing. Now let's talk about something that Einstein felt uncomfortable about and actually wanted to subsume into a larger theory, and that is the quantum theory. Now, the quantum theory is the theory of atomic physics. Electrons dance in our PCs, and the electronic age with fiber optics and lasers are all dependent on the quantum theory. But the quantum theory is also dependent on something called uncertainty, and this is what made Einstein very uneasy. Could you elaborate?
Sure. Heisenberg, a physicist in the 20th century, came up with this so-called uncertainty principle through his research into the quantum theory, into quantum mechanics. And the uncertainty principle basically says that there are features of the micro world that you can't ever know with complete precision. And the best example, the simplest example, is you take one of those electrons that you were just mentioning. The uncertainty principle, when applied to an electron, says that you cannot know where an electron is and how fast the electron is moving simultaneously with total precision. And this has nothing to do with how good equipment you have or how good an experimenter you are. There is a fundamental limit on these features of the microworld in terms of their acquiring definite values. And that's the uncertainty that this principle declares.
Now, some of the greatest geniuses of the 20th century didn't like this formulation. Erwin Schrödinger, the man who helped to formulate the wave function of quantum theory, didn't like this, and he proposed the Schrödinger cat problem to show that this was ridiculous. That if I have a cat in a box and the cat is connected to a gun is connected to, let's say, uranium, and a Geiger counter then registers the uranium disintegrating, sets off the gun, and kills the cat. So far, so good. However, quantum mechanics says that until you open the box, you don't really know what state the cat is in because you don't know what state the uranium atom is in. So in other words, before you look at a cat, the cat exists both simultaneoschly dead and alive. Now, how can you be both dead and alive? Schrodinger thought this was absurd and thought that this was a disproof of the fundamental postulates of the uncertainty principle. But, well, what are your thoughts?
Well, indeed, the Schrodinger cat paradox is so troubling because it takes the bizarre features of the quantum world, which we normally think of as applying to particles, like electrons, and it scales it up and makes it apply to big objects, big everyday objects, like a cat, an example that you are describing. So whereas we don't feel so troubled by saying an electron can sort of be partly this way, partly that way, partly to the left or partly to the right, we definitely do find it very troublesome to say that when it comes to a cat, that the cat is here or there or partly dead or partly alive. It does sound completely nutty. I personally feel that there is a resolution to this paradox or this strangeness that has been developed in the last few decades. And what it does, it recognizes that the conclusion that the cat would be partly dead or partly alive takes into account only the local environment of the cat itself. It doesn't take into account the fact that the cat actually interacts with a global environment. The cat is being impinged upon by air molecules. It's being hit by photons of light and so forth. You can't ever cut the cat off completely from its surroundings. And it turns out, and this is great, when you take the full environment into account, it shows, according to quantum theory, that the mixture of being half dead and half alive goes away. That the cat is one or the other, not both. Now, there are subtleties that, frankly, we still need to work out in this picture, so I don't want to give the impression that it's all fully worked out, but I think that the key feature is you must include the environment. And people neglected the environment for a long time just to make matters simple, to make the math simple. But when you include the environment, things do start to look less puzzling.
Okay, but there's still a question of probabilities, even if you have interaction with the environment.
Yes.
And when we had Steve Weinberg on the air, he mentioned the analogy with sitting in a room with lots of radio frequencies in your room. There are many frequencies, radio frequencies in your room. You're listening to this radio station, but in the room you have the frequencies of all radio stations. But you're tuned into one frequency. So you exist simultaneously in a world with many, many radio frequencies, but you tune into one. See, these other radio frequencies, he claims, are universes. In one universe, the cat is dead. In the other universe, the cat is alive. But you happen to be tuned into one where, because of the interactions with the environment, the cat happens to be alive.
Yes.
But that means that someplace in your room, in your very room, there is a wave function, a radio frequency, of a cat in which the cat is dead. Mm-hmm. Now, if that's true, it means that there are, in some sense, all possible worlds coexisting simultaneously in your living room.
Sure.
What are your thoughts?
Well, that's, in fact, the point when I said that I didn't feel everything had been completely worked out. It's exactly that issue, how to deal with the fact that even if the cat isn't in a mixture of being half dead and half alive, there's still other probabilities of being one half dead and one half alive. And what does that mean? I don't know exactly what it means. I don't think anybody really does, but one proposal certainly is the one that you're describing, the one that Stephen Weinberg apparently described, which is there are multiple universes. And in one universe, the cat is dead, and in another universe, the cat is alive. And when you open the box and, for instance, you see it alive, it means you're tuning in to that particular one. You've entered into that branch, if you will, of this ever-branching tributary of universes. I am a little uncomfortable with that idea. It is so uneconomical to imagine that there are many, many universes out there, and we're just experiencing one of an infinite number. That doesn't mean it's not right. It may be right. I'm open to it being right, but I also think that we need to continue thinking hard on this problem because there may be solutions that don't require this kind of a radical change to our very sense of reality. But if that is ultimately where we are led, I think it's fantastically exciting. If this is really true, then there are many universes out there. That's exciting, but I don't want to go to that conclusion until there is no other possibility, when it's the only one left standing.
Now, of course, in Twilight Zone, they like to play with this kind of idea. In one Twilight Zone episode, a man wakes up and finds out that he never lived in the world. All his friends don't recognize him. He meets his mother and father, and they say that we never had a son. But that means that perhaps the mother had a miscarriage. And a miscarriage is caused by one quantum event, let's say, one cosmic ray that went through his mother's womb, causing a miscarriage, and that's why he wasn't born. So, in other words, one quantum event separates you from a world where you don't exist from a world where you do exist. And Frank Wilczek, who we've also interviewed at Princeton and also in Santa Barbara, he was of the opinion that, we have to just get used to the idea that these other worlds exist. And we also had one of the originators of the inflation theory at MIT, Alan Guth, on the radio. And he said that you just have to get used to the idea that in one universe, Elvis Presley is still alive.
Right. That makes, no doubt, some people very happy. And so you're right. There are many physicists. Frank Wilczek is a great proponent of the many worlds interpretation of quantum theory. There are many physicists who do take this interpretation on board fully. I'm not saying it's wrong. In fact, if I was asked to choose one interpretation of quantum theory and defend it, I think I would probably choose the many worlds interpretation, because there are features of it that really do address key problems in our formulation of quantum mechanics. So don't get me wrong. I think it's a viable and certainly a worthwhile interpretation to study. I just am not sure it's the only one, and I'm not sure it's the best one. And that's why I think we need to keep working.
Okay, now let's make the next big jump, the jump to string theory, which makes the claim of uniting Einstein's theory of space and time with the quantum theory. So you've done this many times before, but could you explain briefly why string theory has this magical property of being able to unify the two great paradigms of the 20th century, relativity of the theory of the very big, and quantum theory, the theory of the very small?
Sure. The basic reason has to do with the uncertainty that we were talking about a little while ago with quantum mechanics. Indeed, Heisenberg showed that when you are studying an electron, it can sort of jitter around because you can't say precisely where it is. And in fact, if you understand the uncertainty principle in mathematical terms, it shows you that the smaller the distance scale over which you examine an electron, the more wildly it jitters, the more wild the frenetic behavior becomes. So the lesson from quantum theory is the smaller you go, the more wild and turbulent the world is. Now, the reason why there's a conflict between quantum mechanics and general relativity is that when you examine the fabric of space itself, on incredibly small scales, the quantum jitter is simply too violent for Einstein's theory to handle. And that's why the theories come into conflict, and that's why they break down. String theory comes along, and the way it resolves this problem is it says that the finest ingredient in the world is a little filament of energy, a little string. And the little string is tiny. It's about 10 to the minus 33 centimeters. That's 100 billionth the size of a nucleus, so it's really small. But because it has a non-zero size, and it is the smallest thing in the universe, you can't examine the world on scales any smaller than a string itself. You can't go any smaller than the smallest ingredient. And that means that the jitter from quantum theory is limited. You can't go to arbitrarily short distance scales, therefore you don't get the arbitrarily violent jitters that we thought you would encounter. String theory cuts it off. It sets a limit, and the limit is just right so that general relativity can cope with the amount of jitter that you can get, and it allows us to marry quantum theory and general relativity together.
Okay, now let's talk about higher dimensions, because some people who believe in string theory say that it's a potential weakness that we can't measure dimensions beyond length, width, and height. Other people say, well, why not? Why not have 10, 11 dimensions? It's a fantastic possibility to expand our consciousness. So tell us a little bit about, what are these higher dimensions, and why don't we see them? Why can't we jump into hyperspace?
Sure. Well, when string theory came along and it put general relativity and quantum mechanics together, it turns out that it did so at a particular price, a particular cost, and the cost is just what you're referring to. The theory works, but only if the world has more than 3 space dimensions, more than left, right, back, forth, and up, down. In fact, the theory needs at least 6, and in fact, probably 7 more space dimensions. Now, that sounds nutty at first, and that brings us to your question. Why don't we see them? And why can't we jump into them? And there are a couple of answers to that. One, which is the more traditional one, an answer that I've worked on for a decade and a half, it's possible that the extra dimensions are very tiny. They're tightly crumpled up like a piece of paper that you crumple to an incredibly small size. And because they're so tightly crumpled, there's very little room in those other dimensions. And therefore, we are unable to go into them because we're too big. Even our most fine equipment, even the smallest particles that we use to probe the universe, don't have the energy to go into this very tiny space. So that's one possible answer why we don't see them. The other possible answer is we don't see them because of the way we see. That is, we look at the world around us and we see things by virtue of the electromagnetic force, light, travels into our eyes, allowing us to see the stuff in the world around us. According to string theory, it's possible that light itself may be trapped in our 3 dimensions, and it can't get off of our dimensions to move into the other ones. Even if the other ones are big in this approach, we can't use the familiar forces of electricity, magnetism, even the nuclear forces to access the other dimensions. It turns out that only the force of gravity will be able to move into these extra dimensions, and so it is our only hope of getting some direct evidence that the extra dimensions are there.
Now, even in high school, when you learn about Newton's theory of gravity, it's based on the inverse square law.
Yeah.
That is, if you double the distance of separation of 2 objects, the Earth and the Moon, for example, gravity goes down by a factor of 4. If you triple the distance, gravity goes down by a factor of 9. And this particular factor is due to the dispersion of the forces of gravity throughout 3-dimensional space. So therefore, if space were 4-dimensional, 5-dimensional, 6-dimensional, you would have an inverse cube, inverse quartic, inverse quintic power, but we don't see that. Therefore, the question is, was Newton slightly wrong, maybe at the subatomic level, in postulating an inverse square law?
He actually may have been wrong. So it's quite possible, if these extra dimensional scenarios are correct, that indeed on big scales, gravity can easily spread out through the 3 big dimensions, and that gives rise, as you described, to the inverse square law because of the way that the gravitational lines of force spread out. They disperse. But maybe on very small scales, scales that are on the size of these extra dimensions, assuming they're tightly curled up, gravity can seep off into those tiny extra dimensions.
Well, I'm afraid that's it for the first part of Exploration. Once again, our special guest is Professor Brian Greene, Professor of Physics at Columbia University, author of the books Elegant Universe and The Fabric of Space and Time. And if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. That's 1-800-735-0230 for a copy of today's program. And also check out my latest book. It's called Parallel Worlds, and it's won a number of science prizes, and it talks about the very latest in cosmology, the possibility of time travel, the existence of parallel universes. So stay tuned now for the second half of Exploration. Columbia University. String theory consists of tiny little strings like a rubber band. Each vibration of the rubber band corresponds to a subatomic particle. And that's why we have thousands of these subatomic particles. They're not particles at all. They're nothing but musical notes on a tiny vibrating string. Recently, however, there's something called M theory being proposed, M for membranes. That's defined in 11 dimensions, and it includes all of string theory. This means that perhaps our universe can now be viewed as a gigantic bubble membrane of some sort, floating in a 11-dimensional hyperspace, and that raises the question, are there other bubble universes out there? And Dr. Randall of Harvard University says yes. Dr. Lisa Randall is the author of the book Warp Passages, and she's an expert on M-theory. And so with Dr. Lisa Randall, we'll talk about this new theory called M-theory. The first question for you, Dr. Randall, is where did you grow up, and how did you first get interested in something as abstract as theoretical physics?
Hi. I grew up in Queens, in New York. I guess I didn't start off interested in physics per se. I like science, but really, when I was a kid, I liked doing math. I think a lot of people have some specific moment or specific teacher that they point to when they say why they became a scientist. But for me, I think it was just the fact that I really did like doing math. I actually very much liked the fact that there were answers, that you knew whether you were right or wrong, and that it wasn't just a matter of opinion. And I don't know if that was because, early 60s were a time of upheaval or whatever, but I really liked the fact that there were definite answers to things.
And was there a particular book, like in Einstein's early history, there was a geometry book that fascinated him?
Yeah.
Was there any thing like that?
I know, it sounds kind of bad, but I really can't think of one specific thing. I think basically I just enjoyed doing it, and I didn't even always have great teachers, but I did have, a couple of good teachers, along the way in junior high school or high school. By the time I got to high school, I really did start getting interested in physics. That's the first time I had a physics class, and we had it in 10th grade, so sophomore year. So by then, I didn't actually know before then that I actually wanted to do science, but at that time, I began to think about it a lot more seriously.
Okay, and what was the transition between math and physics? We've had mathematicians on the program who talk about the internal beauty of mathematics, but physics is quite different in the sense we're talking about the physical universe. So what was the transition between math and physics?
Well, ironically, one of the things that is kind of fun in physics is all the things that you don't know the answers to. So there's all these... although I didn't start off from that direction, I think as I've done physics more, I've gone more and more to appreciate just how many things there are we don't understand and how many things would be very nice to explain. But in terms of what you actually do, I guess I did want to do something that was more applied to the world. Although I enjoyed math quite a lot, I did want to do something where there was some connection to our physical universe.
And theoretical high-energy physics is perhaps the most abstract and the most mathematical of the branches of physics. What led you in that direction?
Well, I guess one of the things I did is I actually really liked model building. So what model building is sort of trying to get beyond, say, what we know from experiments, standard model, but sort of do it more incrementally in some ways. But it involves putting together more or less known ingredients, more or less known physical ingredients. What are the forces, how they act? But trying to go a step further and sort of put them together in a more comprehensive fashion so that we can understand things that we haven't yet understood, like where math comes from, for example. So I think I just enjoyed actually just playing those games in the beginning. And then as I learned more, then I got more into this sort of more formal mathematical aspects of it.
And also, did you have any experience being a woman? If you take a look
I had a lot of experience being a woman.
Right. Any negative experiences, I apologize. If you take a look at any physics conference, basically you see a whole ocean of male figures. How did you feel being a woman in the field of high-energy physics?
It's a funny thing. I think that it's something that I became much more conscious of, actually, in the later stages. I think earlier, certainly in the very beginning, when we were just doing math or whatever, there was no question who was getting more correct answers. That was one of the things that was nice. You couldn't say someone was bad in math if they were getting a better score than you were. So I don't think it was considered that strange. I just was doing what I did. I might have been oblivious, but at the time it just seemed kind of normal. I just was one of the people who did that. As I got into the field, and of course, it's not to say that I didn't notice that there weren't that many women. And certainly by the time I was in college, it was disappointing how few women there were in my classes or that continued with it. And, in retrospect, I realized how it could have been a lot easier if there were more there. But I don't think I didn't recognize it at the time. I think students today actually are much more conscious of how much it does affect their experience. I think I wasn't really fully cognizant of it. I just was doing what I did. I think later on, though, as you get to more advanced stages, oddly enough, it becomes more obvious and has more effect. I think then I felt it more.
But there was no problem with promotion or getting recognition. You felt you were treated fairly by the physics community?
Well, I wouldn't say everything is fair. I mean, I do think there are problems. I think I did well, and so I really can't complain. But I think things might have been easier in certain circumstances. In fact, there certainly would have been easier in certain times. It's really not perfect, and I mean, I just think that it does affect your experience. It can be an advantage. I mean, one advantage is that when you go to a conference, people do remember you. So early on, before anyone knows who you are, that's probably an advantage. But I think there's a lot of ways it works against you too. And they're subtle. It's not a big thing. And certainly, overall things, some things work out, but I don't think things are actually completely fair yet.
Okay, now let's talk about physics, specifically the four fundamental forces, including gravity, which is perhaps the strangest of the four fundamental forces. So could you elaborate about the four fundamental forces and why gravity is rather different?
So the four forces that we now know about are electromagnetism, which most people have heard of, and there's also two other forces called the weak and strong forces that were discovered much more recently. In the latter half of the last century. And we'll talk about those shortly. Those have to do with nuclear interactions, for example, or what holds together a proton. But then there's another force, which is gravity, which, of course, also was known for a long time. But gravity really does seem to be very different than the other forces. And one reason that it's different is just that it's so extraordinarily weak. If you just look at what the masses of particles are, or just what we know about particles, it seems that it's actually inconsistent for gravity to be as weak as it is. The scale is just many orders of magnitude. The mass scale, if you were to associate a mass scale with gravity, it's many orders of magnitude, about 16 orders of magnitude higher than the other masses that we know about in particle physics. And 16 orders of magnitude is something we certainly like to understand. It's just so weak, we really don't know what's going on there. Also, if you extrapolate the three other known forces, aside from gravity, to high energy, it does look like there's some sort of unification. Now, which theory you have determines exactly how precisely unification happens, but it does look like at high energy, the forces were at least of roughly comparable strength. And again, gravity just stands out because it's just different. It doesn't seem to exactly unify with the other forces.
Well, we're running out of time. However, when we get back to the second part of exploration, I'd like to ask you about Einstein, because it was Einstein who had this dream, a dream to create a theory of everything, a theory that which would contain gravity, the electromagnetic force, or light, and even the quantum theory of matter. And Einstein thought that it would allow him to, quote, read the mind of God. So after the break, I'll ask you about Einstein's quest for a theory of everything. Now, Einstein tried to unite gravity with light, with electromagnetism, and that approach, unfortunately didn't work. However, recently, in the last several decades, there's been a lot of work, especially with Steve Weinberg, who was on this program a few months ago, concerning unifying some of these forces. So could you explain some of the progress that we've made since the 60s and 70s concerning unifying some of these quantum forces?
Sure. So one thing is when we look at the various forces, say the weak interactions, strong interactions, and electromagnetism, at the energies that we tend to see things, the energies we experience, they appear to be very different forces. We know electromagnetism gives rise to a long-range force, whereas we know about the weak interactions, for example, lead to nuclear decay. That's one of their places they occur. It also occurs in the sun. But it's a very short-range force. It really seems quite different. And also strong interactions seem extraordinarily different because they're in fact so strong that you can't even isolate the particles that carry the strong force. So ironically, one of the reasons we didn't see the strong force was because it's so strong that we don't see charged objects that are charged under the strong force. Now, this is all true at low energy, but when we go to higher energies, the forces begin to look more similar. And if you go to energies around 100, I measure in GeV, so about the mass of the W or the Z, which is about 100 times heavier than the proton mass. The forces are beginning to look more similar there. They still don't have exactly the same strength, but they all seem to be qualitatively the same. They sort of all look like they mediate fairly long-range force on that scale. But then you can extrapolate to even higher energies. And I should say we actually know a precise procedure for finding out how interactions depend on distance or energy. And if we went ahead and extrapolated to higher energy, we find that in the standard model, all the forces have roughly the same strength. But if you actually go to extensions of the standard model, and we'll talk later about why we might believe there is more to physics than the standard model. And by the standard model, I mean the standard model of particle physics that includes three forces and the known quarks and leptons which interact under these forces. But if we extrapolate to high energy, it looks like the forces can have the same strength, especially in extensions of the standard model. So that does seem to be huge progress in terms of forces being unified, because it really does look like at high energy. These three forces might have the same strength, which means that perhaps they're all manifestations of a single force above that energy.
Okay, now Einstein spent the last 30 years of his life chasing after a, quote, theory of everything. He wanted a theory of gravity, light, and also the quantum theory in his later years, and he failed. However, today we do have something called string theory, which is the leading candidate, in fact, is the only candidate for a theory of all fundamental forces. So tell us a little bit about string theory.
So, although I mentioned the fact that gravity looks different because it's weak, there's another problem with gravity that I didn't mention, which is just that we don't really know completely how to make a quantum theory of gravity, at least certainly not without string theory. It looks like when you try to make a theory that has both quantum mechanics and general relativity in it, you just run into trouble at short distance, for example, because at low energies we usually don't notice this problem because you either are in a domain where either gravity is important or you're in a domain where quantum mechanics is important. And if one is small compared to the other, we don't have to worry about it. But if you go to a regime where both are important, we don't have a theory that certainly the theory without string theory doesn't work. It just seems that both forces are trying to do their thing and they're just incompatible. However, if you have string theory, if you, instead of assuming, like we do in particle physics, that the fundamental objects are particles, which is to say point-like objects, if you assume the fundamental objects are strings, which is to say slightly extended objects that look like strings, it seems that these problems can be ameliorated. We don't completely know how to combine quantum mechanics and gravity because we don't completely know how string theory really works. But it does look like it's a theory that can consistently contain both quantum mechanics and gravity. Of course, it really does that in a theory with many more dimensions of space than we have, 10 or even 11 total dimensions, which is to say 9 or 10 spatial dimensions. So it's certainly gravity, but it's not naively the gravity we expect. And so there are many challenges that still remain, although it does look like it's a theory with both quantum mechanics and gravity. We want to make sure it's gravity as we know it, which means we'd like to understand how we have three spatial dimensions, for one thing. And also we'd like to see it solve some of the problems that a theory that has both quantum mechanics and gravity is supposed to solve. And we still have a long way to go in really fully understanding all of string theory's implications.
Okay. Well, it was almost 30 years ago when string theory was shown to be consistent only in 10-dimensional hyperspace. And I still remember the reaction of most physicists at that point. People began to snicker. They began to laugh. They began to say that this is Star Trek. This is not real science. And the model pretty much died as a consequence of the fact that, well, where are these higher dimensions? We don't see 10-dimensional hyperspace opening up whenever we move in a straight line or we move in three-dimensional space. So tell us a little bit about the process of compactification or rolling up some of these dimensions into something that's very small.
So, of course, if the theory really had 9 dimensions of space that were accessible to us, that we could see, that we could observe, that would be a problem. It's clearly not the world in which we live. So there's a question: can you have a theory that looks like, at very high energy, for example, that it really does have these additional dimensions, but say at the energies at which we experience things or can do our measurements, we just wouldn't see them? And although that sounds a little bit far-fetched, it's actually a very simple thing to actually imagine. For example, when you look at a piece of string, for example, it looks, you know that it's really a 3-dimensional object, but if you hold it very far away, it certainly looks like a 1-dimensional object. You really see it as having one dimension in which it's extended, and the others you might as well think of it as point-like. And that's sort of a general idea that if you have extra dimensions that are somehow curled up or small in size, if you have dimensions that are small, if you look at big, if you're only measuring things with a sensitivity to, say, larger distances, then you don't necessarily see all the structure that there might be at very short distance. So, for example, if you're a bug on the string, you would actually be able to see it as 3-dimensional, or if you're as a person far away, you see it as 1-dimensional. And in a similar way, it's possible that the superfluous spatial dimensions are curled up to a small size, so that everywhere there really are those dimensions, but we just don't see them. We just don't have the resolution to be able to make out the fact that there are those dimensions. And I should say that was sort of the old theory, and it's known as, basically there's a Kalu-Klein theory based on this, when we curl up the dimensions. And actually one of the exciting things that Raman Sundram and I actually found was that there is an alternative, but we can get into that later.
Okay, well, when people hear about 10-dimensional hyperspace, they say, wow, maybe I can jump into my starship and go into these higher dimensions. But then they're rather disappointed when they find out that these dimensions are very tiny, very small, too small for an atom to get into. However, there is something now called M-theory, which is generating a lot of excitement. So tell us a little bit about the differences and the similarities between string theory in 10-dimensional hyperspace and something called M-theory.
Well, M-theory really has string theory in it, but I think what's actually very important that sort of M-theory brought home to us more is that string theory itself isn't just the theory of strings, but actually is a theory that has not just strings, but membranes. And strings are objects that are extended in one dimension, whereas you could have these objects that we call branes, which are like membranes, that are in string theory, and they can be extended in more dimensions. So you can have branes of various dimensionality. Now, what do I mean by that? Well, for example, you can imagine, say, a curtain in your house, which is a 2-dimensional object in a 3-dimensional room. And one reason these branes are important, at least from my perspective, is that there's actually mechanisms in string theory to confine particles to the brane. Now, what that means in practice is that although we know that there are extra dimensions, say, in string theory, it might be that not everything actually explores those extra dimensions. It might be that things like electrons are stuck on a brane. They see all the dimensions. They don't travel there. And if they interact with the photon that's stuck on the brane, the photon doesn't spread out. The electromagnetic force won't spread out into the other dimensions. So branes really not only change the fundamental nature of string theory, because it's not just strings, but they also change our idea of what things would look like if these extra dimensions exist. Because rather than say that everything has to be going through all of the dimensions, it could be that various particles only experience a fraction of the dimensions, and there could even be other branes that hold other forces and particles that we don't detect at all if we're stuck on our brane.
Okay, now M-theory is defined in 11-dimensional hyperspace, one extra dimension, yet we live in a 3-spatial dimensional universe plus time. So could you explain to us how the rolling up process is done, and
how the what process?
How the rolling up, the compactification process works, and how some of these dimensions could be rather large. They don't have to be small at all.
Well, okay, so let's go back to just rolling up the dimensions. And, M-theory just has one more dimension than string theory, which already had way too many dimensions. So basically with M-theory, you have to roll up one more dimension. But so the picture we had before was that one reason you don't see the other dimensions is because they're curled up to such a small size you can't actually detect them. And we just mentioned, however, that there's another reason you might not see extra dimensions, which is that particles could be stuck on a brane. Now, I should be careful when I say particles can be stuck on a brane, because it's important to keep in mind that basically we know mechanisms to trap most particles on branes, but we don't actually have a mechanism to trap gravity onto a brane. So gravity is always connected with the entire space. In fact, Einstein has told us that gravity is connected with the geometry of space. So it wouldn't make sense to say that gravity is stuck on a brane. But it does make sense to say electromagnetism, for example, is on a brane. Now, what that would mean is that whereas before we might have said, well, so let's suppose we ask ourselves, how big can the extra dimensions be? Well, without branes, we would have said for a limit might be set by the fact that if electromagnetism was spread throughout an extra dimension and an electron lived in an extra dimension, we would actually see consequences. And if we ask ourselves, we've tested up to energies about 100 times the proton mass. So if we say that we know everything that's going on in energy up to that energy, we can actually set a limit on what the size of the extra dimension would be. And although it might sound very stringent, in some ways it's not as bad as you might have thought. It's about 10 to the minus 17 centimeters. The reason I say it's not as bad as you might have thought was based on just gravity itself. You might have thought it was 16 orders of magnitude smaller. But that bound that I just gave you, and that's a very small, 10 to the minus 17 centimeters, isn't the same bound that you would get if you have branes. Now, the reason for that is if you have branes, then electromagnetism can be stuck on the branes, and that means they don't travel in the extra dimension. So before, actually, one way that we could have ruled out having dimensions that were bigger than 10 to the minus 17 centimeters is we would have said that there would be partners of the electron that carry momentum in those extra dimensions, and we would have seen them. And we haven't seen them. But if the electron is stuck on the brane, then it's impossible for a partner of the electron to have momentum in the extra dimension. It's stuck on the brane. It just never goes into the extra dimension. Now, what that means is that the size of the extra dimension is only constrained by the things that actually travel in the extra dimension. And if you want to have the weakest bound possible, you can have everything bound on the brane except for gravity. And then the bounds on the size of the extra dimension have to do with how well we study gravity. And the fact is we haven't studied gravity all that well. We actually only know about gravity down to distances of about 1/10 of a millimeter now, which means that if we have a brane, we can actually get away with much larger dimensions than we thought. And actually, so it's even more dramatic than that if we have branes, and this is some of the work that Raman Sundram and I found. Because if you have a brane, from Einstein we know that if you have energy anywhere, it will affect what gravity looks like. And what we found is that you can have a scenario with a huge brane sitting in with one extra dimension, for example, in which gravity stays highly concentrated near the brane. So whereas before we used to think gravity just has to spread out everywhere equally, if you have branes, you then start distinguishing some directions from others. So not only is there this effect that you can actually have things stuck on the brane, but you have another effect of branes, which is that they affect the gravitational field itself. And we found that itself allowed an infinite extra dimension. You can actually have a fifth dimension of that is infinite in extent. And you would have thought that was ruled out because gravity would spread too much into that extra dimension. But we actually found that isn't necessarily the case when you have warped or curved geometry. So branes really do introduce some very dramatic new possibilities.
Okay, well, in the past, when we've had some string people on the show, I would ask the key question, and that is, can you test string theory? And at that point, of course, we have a lot of hemming and hawing and statements that, well, you would have to create a universe in your basement. You would have to have an atom smasher the size of a galaxy to test string theory. However, now you're actually proposing ideas which can be measured in the laboratory, that is the strength of gravity, and perhaps the presence of other universes. So tell us a little bit about how the fact now that M-theory gives us a new picture, which may now give us some experimental data that we can fit the universe with.
So what's very exciting, just to take a step back, is what we learned with extra dimensions and brains is not just that there are new possibilities for how things can be hidden. We've also found that with brains and extra dimensions, there are actually possible implications for particle physics. That is to say, physics at energies where we measure things and know things and know about puzzles, in fact. So if these extra dimensions have connections to particle physics, then, as you might expect, there actually would be visible consequences. So one problem in particle physics that extra dimensions seem to address very beautifully is a problem that is called the hierarchy problem. And essentially, that is the problem of why gravity is so weak. It just seems even almost inconsistent for gravity to be that weak if we just had standard 3+1 dimensional physics. The nice thing about extra dimensions is that they give you very beautiful reasons why gravity is so weak.
I'm afraid that's it for Exploration. Once again, our special guest has been Dr. Lisa Randall, professor of physics at Harvard University and author of the book Warp Passages. And if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. That's 1-800-735-0230 for a copy of today's program. And also check out my latest book. It's called Parallel Worlds, the very latest in cosmology, the whole question of string theory, M-theory, time travel, parallel universes, all of that contained in my book, Parallel Worlds. Also check out my website. It's www.mkaku.org, mkaku.org. And so far we've logged over 110 million page hits on that website. Good day.